The graphing calculator can be a really handy tool to use when you need to find the derivative of a function that you don't yet know how to work with algebraically. So I have a function like that before us. This is a function that, at least at this point in the course, we don't know how to work with algebraically. Sine x all cubed. X is in radian mode, by the way, and we're going to look at the function on the interval 0 to pi. And we're going to want to do these three things. Find the slope of the tangent line, draw the derivative graph, and go in reverse and find the values of x at which a given derivative value occurs. Just to show you how we've entered that function, under y equals, it's sine x, all in brackets, cubed. Under mode, we need to be sure we're in radian mode. And just so that it fits nicely on the screen, under my window dimensions, I've set my window to go from 0 to pi because that's where I'm being asked to look. And the y values are between -3 and 3. And so I get a function graph, as you can see. Now the first thing we want to look at is the slope of the tangent line at x equals 1, which visually we know is something approximately like this. And we want to come up with the slope of that line. So there's a couple of ways I can do this with my calculator. One way is to simply go second function trace, which is the calculate menu, go down to number 6, which is the derivative, enter the x value at which you want the derivative, x equals 1, press enter, and you'll see that it says that the derivative at that point is 1.148 rounded off. Alright, now there is another way that I recommend over this. This method usually works quite well and it's nice and visual, but a secondary way to do that is to enter the following, and I'm going to write this out first because depending on which calculator you have, the syntax may look different. So I'm going to write numerical derivative. That's the command I'm going to be looking for. And you will need to enter 3 arguments. The first argument is the function. Well, that's entered in y1. The second argument is what the function is with respect to. It's with respect to x. And the third argument is the value of x at which the derivative occurs, which is 1. Alright? Now if you have a newer version of the calculator, what you're going to do is enter it this way, which is more traditional syntax. The derivative of y1 at the point where x equals 1. Alright, and the calculator I have actually uses the newer syntax. But where you find these commands is the same on both calculators. So off to the calculator I go, and I'm going to go to a blank screen, which is second function quit. And to get these commands, we go off to math. You scroll down to number 8, math 8. And if you have the older version of the calculator, it will write out n deriv bracket, and you can enter these 3 arguments and close the brackets. For me, I'm entering this syntax. So it's the derivative with respect to x of y1, y vars, at the point where x is equal to 1. And when I press enter, 1.148 is what I get. Alright, the next thing I want to look at is finding the derivative graph for a given function. And remember that the derivative graph, the y values of the derivative graph, represent the slopes of the tangent lines at the corresponding values of x to the original function. So for example, if I take this point halfway between these 2 markings, the slope of the tangent line here is 0. So that means that the y value on the derivative graph would be 0. Okay. Over at x equals 0, it seems as though the derivative is probably about the same. And as I move from this point to this point, and as the tangent lines move, they get larger and then they get smaller. So my derivative graph would have slopes that get larger and then get smaller. Okay? Again, the y values of the derivative graph are the slopes of the tangent lines to the original graph at the same value of x. And as we move to the to the right of this point, the slopes become negative, and then they balance back to becoming more positive. So I'm expecting my derivative graph to look something like that. So that's just a sketch based on what I'm able to work with here. But let's use the calculator to get a better picture of what the derivative graph would look like. Alright, so to do that, what I'm going to do is I've got my original function entered into y1 as so, and into the second function I'm going to enter this command. Again, depends on the version of the calculator you have. The derivative of y1 with respect to x, and at which point? Well, at all points, because we want the entire graph. Or if you're using the other version, the newer version of the calculator, you're going to enter where x is equal to x. Alright, so let's enter our command. We're set up at y2. We're going to go to Math 8, and we're doing the derivative of x, the derivative of y1, at the point where x is equal to x. And just so that this shows up a little darker than the original function, I'm just going to backspace and bold this. And here comes the derivative graph. Let's see if it matches the one that I created by hand, and it's looking pretty close. Wonderful, and we've created the derivative graph. So if I wanted to know the slope of the tangent line at a given point, let's say at x equals 2, okay, the calculator is showing me the y value on the original graph. If I arrow down, oh, it moved a little bit. Let's just type that again. 2. The slope of the tangent line to this graph right here, that tangent slope there, would be negative 1.03, because the y value of the derivative graph is the slope of the tangent line to the original function. Okay, the next thing I want to look at is points where the function has tangent slopes at a given value, in this case particularly negative a half. Well, a slope of negative a half is a line that falls fairly gradually. So if I look at where that might be on this graph, I might take that up, say, well, there might be a tangent point, you know, somewhere in this neighborhood. Okay, so I'm going to look for that. So what I can do, since I have the derivative graph, and since I'm looking for where the derivative is equal to negative a half, I can simply go up to my derivative graph, and negative a half would be approximately there. And if I just go across, I can see that, oh, well, maybe there's more than one point where that happens. Okay, and if I go back to my original function, make a copy of that, there might actually be another point a little bit further down where the slope of the tangent line is also negative a half. So all I need to do with my calculator is find the point of intersection between the derivative graph and y3 equals negative 0.5. So here on the calculator, I just have the y2 showing up. I've turned function 1 off because I'm focusing on function 2, which is the derivative, and function 3, which is making my derivative, specifically negative 0.5. I'm graphing those two, and then with my intersect button, second function trace, I can find the point of intersection between y2 and y3, and that's coming out to 1.743. And then I could see that there was another value. So going back to my calculator, I can find that intersection point. .698. Now if I actually wanted the coordinates of these 2 points back on the original function, I could plug these two x values into the original function to get the corresponding y value. Now just one final thing to show you with respect to this. An alternate way that you could solve this equation would be to take the derivative, and I'm going to bring the negative 0.5 to the other side and set it to 0. So if I actually look at this function and find the zeros of this function, I should get the same solutions that I got from the previous method. So instead of putting my derivative and specific slope on one line, I could simply take out the y3, and up on line 2 I could just add on to the end plus 0.5. Now what that's going to do is going to shift my derivative graph. It's going to translate it up 0.5 of a unit. And so what I'll look for in this case are these two x-intercepts. And those two x-intercepts right there will turn out to be these two values.